Hi students, hello everyone. Now in this class we are going to study about the characteristics of equilibrium constant, related numerical, Gibbs free energy and equilibrium constant relationship. Now let's discuss about first characteristics of equilibrium constant. In the previous classes what we have studied, let me remind you all. We have already studied the equilibrium introduction, in which we have studied equilibrium in physical and chemical process. We have already studied the graph related to that. And after that, in the previous class, we have studied the law of mass action and the numericals related to that, Kp-Kc relationship and the numericals. Now in this class, we are going to start with the characteristics of equilibrium constant. Okay, so what are the characteristics of the equilibrium constant, which is defined as K? Now, how it is useful in your chemical reactions? What are the applications of these? So, let's understand. If the reaction is reverse, then the value of equilibrium constant is reverse. Suppose any reaction is given and you are just simply reversing that reaction. You are writing in a reverse manner. So the value of equilibrium constant will be simply reverse. If the equation is divided by 2, the equilibrium constant is a square root of k. You have divided the equation by 2. Now the equilibrium constant value, this would become the square root of k. If the equation is multiplied by 2, the equilibrium constant is the square of k. Simply the square of k, that would be the equilibrium constant. If the equation is written in two steps like k1 and k2, then k1 and k2 equals to k. Now the value of equilibrium constant will not affected by addition of catalyst. Equilibrium constant will not depend on the catalyst. It will not be affected by the catalyst. Now let's do some numericals. Given that at 1000 Kelvin, 2SO2 plus O2, it is forming 2SO3. K value is given 261. Calculate K for the following equations. For the following equations, like simply you have reversed this equation, 2SO3 is forming 2SO2 plus O2. So if you have reversed the equation, so we have studied, just simply do what? Just simply do the inverse of the K, as we have studied this thing. Just here it is given to you. What it is given, let's understand about it. Firstly, the value of equilibrium constant is reverse. Reverse, what you need to do for the reverse? For the reverse, you are doing the simply thing, reverse value 1 upon k. So for the A option, 1 upon k you will do. So for the 1 upon k, like 1 upon 261. So for the 1 upon 261, once you will calculate what the answer you will get the 0.0038. It's very simple. Now for the B, SO3 in a equilibrium with the SO2 plus half O2. So now calculate the K value for this reaction. So here firstly, for this is your main equation now. You are doing a reverse, and after the reverse you are doing what? You are dividing by 2. Once you are dividing the equation by 2, it would become the square root of k. So what it will become? 1 upon under root of k. 1 upon under root of k, what is the meaning of this? Under root of 261. So this would become, firstly, under root of k, just calculate this value. Under root of 261, just calculate under root of 261, we are getting what? 1 upon 16.15. So 1 upon 16.15, what would be the answer? Here you have 0.0619. This would become like that. It's very simple if you will try. C, SO2 plus half O2. This is forming SO3. So what is your main equation? This is your main equation. So let's understand. Firstly, you will do the reverse of this reaction. If you want to get this equation from this equation, what you need to do? Firstly, you need to do what? Simply here it is given. No need to reverse for this one. Here simply dividing by 2. If you are dividing this equation by 2, you will get this one. So if you are dividing by 2, then what the answer you will get? 1 upon under root of k. Here you have, but for this C value, you need not to do for this one. You have simply what? SO2 plus half O2. So you need not to do the reverse. Any kind of reverse is not needed here. Under root of k would become, so under root of 261. Under root of 261 will give you 16.15 answer. So these are the values of the k. Consider the following equilibrium: SO2 plus half O2, K1 SO3, 2 SO3, K2, 2 SO2 plus O2. What is the relation between K1 and K2? K1 and K2 relationship is what? K2, can I say, if you are doing the reverse of the K1, if you are doing the reverse of the K1, so what you will get? Let's understand about it. Simple reverse of K1, 1 upon K1 it will become 2. Once you are multiplying the equation by 2, what do you need to do? Simply just square. So here you can say that what is the relationship between the K2 and K1? 1 upon K1 square, that will be equal to the K2 value. Clear? So this is the relationship over here. You can just simply try for this now. Here you have simply just reverse the equation SO3 and it will give you SO2 plus half O2. Now what you are doing? Just multiply by 2. So if you will multiply by 2, 2 SO3, this will give you 2 SO2 plus O2. Clear? Now here we can easily understand 1 upon K1 you will do, and for twice you need to do the square over here. Now the equilibrium constant of the reaction at 426 degrees Celsius is given to you 55.3. What will be the value of equilibrium constant if the reaction is reverse? If you are doing the simply reversing of a reaction, what will be the equilibrium constant value? If the reaction is represented in this way, then what will be the equilibrium constant? So if you are simply doing the reversing of a reaction, if you will reverse the reaction, equilibrium constant for the reaction, for this reaction H2 plus I2, it is given this. Now if you will just inverse the reaction, then what you will get? Let's understand about it. If you will just simply reversing the reaction to HI, it will form the H2 plus I2. So here you have value 1 upon 55.3. So 1 upon 55.3. What will be the value? 1 upon 55.3, 0.018. This will be the value for this. For the B option, if the given reaction is represented in this way, 3H2 plus 3I2, this will form the 6HI. Then what will be the equilibrium constant value? Let's understand. Just if you are multiplying this equation into 3, then what you will get? Then what you will get? Simply this is your basic equation. If you are multiplying by 3, then what would happen? K1 whole cube. This would be your final K2. K1 whole cube. This would give you the answer. So here the K1 value is given to you 55.3. Just to do the whole cube. This will give you the K2. So 55.3 power 3. So 1 69112.37. Completely. Now I hope you all are clear up to this. Now after that, what we have? Types of chemical equilibria. Types of chemical equilibria are two types: homogeneous equilibria and heterogeneous equilibria. Homogeneous equilibria, all the reactants and products are in same phase. Once you will see this reaction in which all the reactants and products, they are in the same phase. Like you will see all the reactants are in gaseous form, product is in gaseous form. So all the reactants and products are in same phase, like all in our gaseous form, all in our solid, all in our in liquid aqueous form. Now heterogeneous equilibria, all the reactants and products are not in a same phase. Ammonium chloride, when heated up, it will give you the ammonia plus HCl gas. Now here ammonium chloride is in solid state. Ammonia and HCl is in gaseous form. So here all the states are not same, they are different. So this type of equilibria is heterogeneous equilibria. Now calculation of degree of dissociation from vapor density measurement. Degree of dissociation you are expressing in terms of alpha. What is the meaning of degree of dissociation? How many number of moles dissociated from the total number of moles taken? Suppose you have taken the 1 mole of any species. From that 1 mole, how many moles are dissociating? That is your degree of dissociation. Degree of dissociation is expressing in alpha terms, number of moles dissociated upon total number of moles taken. PCl5 when heated up, it will give you PCl3 plus Cl2. This is a reversible reaction that has maintained an equilibrium already. 1 mole of PCl5 you have taken. Now from that 1 mole of PCl5, what is the degree of dissociation? Let's understand about it. Before dissociation, what are the total number of moles? That is 1 mole. Total volume, how much it is? V liter. Capital D is the vapor density of PCl5 before dissociation. Before dissociation, PCl5 vapor density is what? It is expressing in terms of capital D. Now, vapor density and volume relationship, that is inversely proportional to the each other. Vapor density is inversely proportional to the volume. Clear to us? Yes. Now, vapor density is inversely proportional to the volume. You are clear with this? After dissociation, from 1 mole, suppose X moles are dissociating, they are converting into PCl3 and Cl2. Okay. So after dissociation, total number of moles, how much it will? Let's understand. Before dissociation, 1 mole of PCl5 is there. Products moles are 0. We are observing, suppose alpha moles are dissociated. So at equilibrium, how many moles are present of PCl5? From 1 mole, alpha moles has been dissociated, like they have converted into PCl3 and Cl2. So how many moles are there at equilibrium of PCl5? That is 1 minus alpha will be there. How many moles of PCl3 and Cl2 will form? Let's understand. There is a relationship, that is 1:1:1. So from 1 mole, 1 mole, 1 mole is there. So if alpha mole are dissociating, so here alpha mole of PCl3 and Cl2 will be formed. Can we understand this thing? Yes. So how many total number of moles are at equilibrium? At equilibrium, 1 minus alpha plus alpha plus alpha. So this would become 1 plus alpha. 1 plus alpha, 1 plus 2 alpha minus alpha. This would become 1 plus alpha. These are the total number of moles. Total volume occupied by the reaction mixture. How much total volume occupied by the reaction mixture? How much it will be? As we know that for 1 mole is present in V liter. 1 plus alpha mole, how much volume they would occupy? 1 plus alpha into V. 1 mole is occupying V liter. So 1 plus alpha moles will occupy how much volume? 1 plus alpha into V volume they would occupy. If small d is the density of the vapor, okay, then we can easily understand after dissociation, vapor density, what is the relationship? Small d is inversely proportional to the 1/1 plus alpha into V. Vapor density is inversely proportional to the volume. So small d is inversely proportional to 1/1 plus alpha into V. Dividing equation 1 by 2. If you are dividing the equation 1 and 2, equation 1, capital D by small d equals 2. Here would be 1/V. Capital D is 1/V. Small d, what is the value for this? 1/1 plus alpha into V. Capital D upon small d, this would become equal to 1 plus alpha. Okay. Now, alpha value you have calculated, capital D minus small d upon D. So, capital D, vapor density before dissociation, vapor density after dissociation. Before dissociation, vapor density, that is representing your theoretical molecular mass. It is like your PCl5 has not been dissociated. Okay, it is not dissociate into PCl3 and Cl2. So before dissociation, vapor density is given to you like capital D, theoretical molecular mass, which has been given over here. Okay, so you have written here theoretical molecular mass minus Observed molecular mass is what? Once it has been dissociated, it is converting into PCl3 plus Cl2. So we are observing that here some mass has been reduced. So here if some mass has been reduced, like some vapor density has been reduced, has been changed, so we are observing, this is my observed. After the reaction, we are observing after the dissociation. So after the dissociation, vapor density would be expressed by small d. After the dissociation, observed molecular mass MO upon MO. So this is what calculated molecular weight, like it is given to you. PCl5 molecular weight you can easily calculate by its atomic mass. Okay, so this was your initially theoretical mass, and vapor density has been calculated according to that. M naught is the observed molecular weight. Observed molecular weight is representing like after dissociation how much mass changes there of PCl5. Okay, that is your observed molecular weight. Now the vapor density of N2O4 at certain temperature is 30. Now calculate the percentage. Now calculate the percentage dissociation of N2O4 at this temperature. Once the N2O4 is heated up, it will give you the NO2 nitrogen dioxide. This reaction has maintained an equilibrium with each other. Now, molecular weight of N2O4, what is that? That is 92. So here we can understand for the N2O4, 14 into 2, 28 plus 64, this will give you 92. Complete molecular weight. Vapor density before dissociation, that is 92 by 2, like 46. Let the degree of dissociation be x. We are assuming that degree of dissociation for this N2O4. How much amount is given? 92 molecular weight is given. Now we are assuming that degree of dissociation, like how much N2O4 is converting into NO2, that degree of dissociation consider as x. Small d, that is equal to the 30. Vapor density of N2O4 at a certain temperature is given 30. So what is the meaning of this? Like reaction is taking place. So at any temperature you have found the vapor density is small 30. So a small d, that is given to you 30 after dissociation. So here you can easily calculate the degree of dissociation, capital D minus small d upon d. Capital D would be what? Vapor density before dissociation 46 minus after dissociation 30. After dissociation 30. 16 by 30.533. That is your degree of dissociation. Degree of dissociation in terms